You see, I see, I'm... Okay, now seems it works, but now this doesn't correspond to that. Okay.
नहीं वैसे कुछ नहीं कि वाईफाई के साथ कनेक्ट है तो ठीक है
Okay. Okay, so the introduction I think is working. The introduction is about the motivation, the research, so which is based on the consideration that building trades are great contributors to environmental pollution, and so we want to reduce the environmental impact of the construction process by using innovative materials, and particularly concrete reinforcement with aggregates or fibers obtained from waste plastics. So the concrete reinforcement with recycled fibers stands as a low-cost technique that allows us to obtain different positive results. To improve the thermoelectrical insulation properties, the fire resistance, which is something not easy to understand at the first glance, to increase markedly the compressive and tensile strength, and also the structural ductility of the material. The materials that we have examined in this study, they were not obtained to 3D printing, they were obtained through industrial processes or manual processes that we will describe. In this first part, for the reinforcement of concrete, we used recycled PET and PP fibers. Those recycled fibers were obtained through an industrial process of extrusion of flakes obtained from the recycling of PET bottles. The water bottles are made of PET, and by processing flakes obtained through the grinding of plastic bottles, and we obtained some fibers through an extrusion process, starting with flakes obtained by grinding of plastic bottles. We obtained fibers that we mixed to concretes and for obtaining some samples of fiber reinforced concrete that we name rPET reinforced concrete, with where the R stands for recycled PET fiber reinforced concrete. And the PET fibers that we examined were of different kinds. We examined the straight fibers, also crimped fibers or embossed fibers. All those fibers were obtained by changing the die of the extruder that processed the flakes, the PET flakes. This is the extrusion line that we used in the plants of extrusion industrial companies in the northern Italy, which are into the business of extrusion of plastic filaments from virgin or recycled material. So those are parts of the extrusion line. And the fibers that we examined were of three kinds for what concerned the PET fibers, and one kind concerning PP fibers, polypropylene fibers. The PET fibers had circular cross-section and were straight or crimped, and the diameter was, those diameters are more considerably thick, and because of the fact that those fibers are intended to be mixed to a concrete, not a mortar. So the diameter is of 1 millimeter, about 1 millimeter, 1/10 or 0.7 millimeters. The length is 40 millimeters, 52. Those are values of tensile strength that we obtained for those fibers, which are different each other depending on the process of extrusion. During the extrusion process, you can apply you can modify the mechanical properties of the material through some pre-straining of the wires. So by applying some pre-straining, you can vary the mechanical properties. And so we had several fibers with different mechanical properties and with different ultimate strain. There was a first kind, high strength fiber, and the second kind was instead less with a lower tensile strength, but similar ultimate strain. So those were the fibers that we examined. PETI are straight fibers, high strength straight fibers. PETB are again straight fibers with those considerably lower tensile strength. PETC were crimped fibers. All those fibers were made of recycled PET. And finally, we had some PP fibers which show the embossments on the lateral surface. Then we mixed those fibers to a concrete. There were people in concrete, I don't know if they are here today, but people expert of cementitious materials. Anyway, we used this concrete with a water to cement ratio of 53, and also fluidifying agent to increase the workability. And so this is a ratio that we have to consider in order to mix concrete with plastic fibers with quite high water to cement ratio is needed for that reason. And this is the composition, the design, the mix design of the concrete that was analyzed. It was with a Portland. It was a Portland cement-based concrete. So some terminology, some notation. UNRRC is a plain concrete, unreinforced concrete. RPTFRCA is concrete reinforced PET fibers at 1% fiber volume fraction. This is the fiber volume fraction that we always considered. So we have RPTFRCA, B, C, depending on the fibers that we employed. And PPFRC is a concrete reinforced with PP fibers, always at 1% fiber volume fraction. So we mixed the concrete with the fibers. Those are the PETC fibers, the crimped fibers. We are actually producing, I can see, wow, it's almost done. We are producing a fiber anyway. Nice. So those fibers were mixed to the concrete paste and then used to form cylindric prismatic specimens with 6 by 6 by 24 centimeters prismatic specimens. And those are the specimens that were prepared. And then I'm showing you some experimental results. First results were focused on the thermal conductivity of the material, because the use of plastic fibers in concrete also is positive also because it leads to increase the thermal resistance, to reduce the thermal conductivity and to increase the thermal resistance of the material, which is good for an environmental reason, because as you can imagine, the use of concrete, if the employment of such concretes for the manufacturing of walls or the external walls of a building will increase the thermal resistance of the wall and will lead to reduced use of heating or air conditioning in winter or summer. So this is also another positive goal, or another goal of the project, to increase the thermal resistance of concrete. So for this for the thermal tests, the prismatic specimens of 20 by 20 by 3 centimeters were inserted into a measurement chamber and subject to heat transfer through a system that is also present in this lamp, to a standard system for measuring the thermal conductivity. And what we obtained was, what we observed is that the thermal conductivity was reduced, sensibly, markedly reduced by mixing concrete with plastic fibers. This is this FRR, which will be shown in different tables, is the fiber reinforcement ratio. So it's the ratio of the property, the percentage variation of the property with of the property of a given property in presence of fibers as compared to the same property in the unreinforced concrete, so in absence of fibers. So this means that if we have minus, so they are not particularly useful in compression, while they work well in tension, and so in bending they show their better performance, their best performance. But what we observed is that by performing compressive strength tests on 15 centimeters cubic specimens, we observed that surprisingly we also increased the compressive strength of the material through reinforcement with 1% fiber volume content, 1% volume content, volume ratio of fibers over concrete. And so we observed a quite remarkable increase in the compressive strength in most cases, in most of the fiber reinforcement specimens that we analyzed. And so the fiber reinforcement ratio, was this the variation of the property due to the addition of fibers was plus 35% in RPT-FRCA, which was which were the fibers with the highest tensile strength. But we observed also an increase in 22% increase in RPT-FRCB, and more reduce the increases in the other materials that we, fiber reinforced concretes that we examined. It must to be pointed out that the reinforcement of concrete with those very positive results originate from the fact that we use a weak concrete. So if you use a weak concrete, the reinforcement with plastic fibers is particularly effective. If you use a strong concrete, that is not the case. You will have a reduction of the compression strength, for example. You will always have some increase in the tensile strength because the concrete is a brittle material, so doesn't carry significant tensile stresses. But in terms of compressive strength, those nice, interesting results are due to the fact that we are using a weak concrete. So the plastic fiber reinforcement of concrete is particularly effective in all cases where we use a weak concrete, which happens many times. In most developing countries, the concrete is not particularly performing, and so in those cases the addition of fibers, which is not such a particularly complicated task, since you can also have a plant for the production of fibers within the construction site. You can have you can include a line for the production of recycled plastic fibers within the construction site, and so you can mix easily concrete with the plastic fibers, obtaining also significant results in terms of compressive strength. This is a picture of a test. This is one specimen broken after the end of the test, and this is a picture showing the fibers within the specimen that was tested. In terms of bending performance, bending tests, we performed on those specimens of 15 centimeters by 60 centimeters, the prismatic specimens. We tested such specimens under 4-point bending tests, and we initially made a crack, a notch in the specimen. Is it terrible? Yeah, it's a bit gross, but it's this is a cookie, a fractal fiber. Yeah. Wow. Yeah, we have made it pretty thick in order to nice. This is the support. You have the support. Anyway, we'll continue, and then we will see the fiber when it's ready. Universal test machine for this. We measured the crack tip opening displacement by averaging the measures of the two transducers placed on the two faces, and so we obtained the crack mouth opening displacement or crack tip opening displacement, and averaged between. You can measure the displacement of the tip or at the mouth, and you have two different displacements, but the most important one is the crack tip, so the displacement of the tip of the that needs to be applied to the specimen in order to perform the test according to international standards for bending tests on concrete specimens. This is a crack mouth opening displacement measurement, crack tip opening displacement measurement. And this is a picture showing the configuration after testing of one specimen reinforced with RPTA fibers, the ones with the higher tensile strength. And you can see the strong bridging effect played by the PAT fibers. Usually when you, I don't know if you're an expert of bending tests on concrete specimen, usually what happens in a bending test on a concrete specimen that it immediately collapses. It immediately breaks into pieces when you reach the critical load, the fracture, the critical load for crack strength, first crack strength of the material. While in this case you have a completely different response. You have such a kind of ductile response after crack propagation. And actually, if we have internet, which I'm not sure, but in case we have internet, yes, we can show a movie of this test. I can show you a movie of this test. Wow, it's very nice actually. Yeah, let me first comment on this. Wow. This nice fractal fiber. See? It's also a decor, can also be a decor. Yeah. So far we were more able to test bars than fibers, because to test fibers you have to go, you have to use a finer resolution, and so this was not possible this far with a 3D printing machine. But we will make more fibers later, and actually you will make with us. This will be the training test, and if you cannot 3D print the fiber, you won't get the diploma of the class. Okay. Just kidding. So, seems that I am not connected. You have to repeat.
Where is your Wi-Fi?
Where is the airplane? The airplane. Because it's an airplane mode. It goes to airplane mode when. Yeah, it says connect.
And why is this is airplane mode?
You go, yeah.
Now it's deactivated.
We do this.
Again, please
Yes, it seems it's browsing the web. Hopefully. So maybe you in India can help us in pushing forward this project, because we had some, yeah, I will tell you why. We were pretty much not available. That's what it's saying, it's not available. It's connecting. Maybe the phone has to be close to the. No. So let's try once again. I turn it off.
Why is your airplane mode is activated?
No, it goes back and forth when you disconnect.
This is not my.
Student, which is not.
Good idea.
Before I go. Yes. Adminis. No, it's trying.
This shows connected.
Oh, so let's try. You might be right. There was a nice movie of this test that I wanted to show you. The first day he worked fine, but now let me see if I can find it. Oh. This doesn't work. It says that it's connected, but then it is not. Sometimes, let me do this. Let me restart the computer.
I think now it's connected.
It is connected.
I think this shows two connections.
Yeah, this other one, I don't know. Let's try this other one. Okay, probably this is connected. No. Okay, I think I have found something. I don't need the, probably I don't need the internet. Hopefully. Okay. So this is a long version of the movie. The movie goes along the wall test, and you can see you can see I can speed up the movie. You see the formation of the crack, the propagation of the crack. There is a pre-crack, and you see that this is the first crack load at this point. See? And usually what happens in those conditions is that immediately the specimen breaks in two pieces. But in this case, what we observed was that the crack didn't go through completely. There was some residual load capacity of the specimen. Then now the transducer is felt apart, and then this is a specimen again. It wasn't possible to break it into two pieces. We were not able to do this. consider how large is this crack. So the result was pretty good. The result was obtained with the high strength fibers, the RPTA fibers, and the bridging effect was clearly visible due to the presence of fibers. This is another specimen, the specimen with the RPT-C. The RPT-C were the fibers, the crimped fibers. So we modeled through an exponential load the experimental observation of the force crack tip opening displacement curve for each material, and we obtained those curves. So the marks indicate the experimental points, and the solid lines indicate the fitting of the experimental points through exponential models that I have described before. So what we observed was that the material with reinforced with RPTA fibers showed the highest first crack load, and also the highest residual load capacity, residual strength capacity. And this kind of response, post-peak response leading to a plateau with non-zero residual strength, was also showed by almost all the specimens with the reinforced with RPT fibers. In this case of the crimped fibers, we observed also a kind of hardening response after the load drop, and then again a decrease. And this is the response of the unreinforced concrete, which is dramatically brittle. I don't have a movie of the brittle specimen because actually it was very fast. But you can believe me that in this case, basically the load goes quickly to zero. The specimen breaks into two pieces, and the load goes to zero very fast. So this is the first crack strength, which is according to the standards, is related to the load that produces the first crack propagation, multiplying by the length of the displacement and divided by the cross-section area with this normalized in this way. You have to reduce the I80 from the H. The H is the height of the specimen. You have to decrease to subtract the initial crack length to the height for defining the crack strength. And then we defined the ductility indices. Ductility indices are basically the ratio between the equivalent, the post-failure strength, so the residual strength, and the first crack strength. The first crack strength is in correspondence to the peak load, while those other quantity, F equivalent 0.06 is the residual strength in the 0.6 millimeters crack opening displacement regime, and this other one is the 0.63 millimeter crack opening displacement regime. Those are the residual strength, and if you divide the residual strength by the first crack strength, you obtain what is called the ductility index. And there are two ductility indices that are shown in different slides. One is referred to the first cracking regime, and the other one to the ultimate cracking regime. And so by measuring those two quantities with the equivalent ultimate loads in those regimes, in the first cracking regime, in the F for those two quantities, F equivalent 0.6 and 0.63 were obtained by basically measuring those two areas, the areas underneath the first crack tip opening displacement curve, and by normalizing those areas through such formula. But basically those quantities are the measure of the residual strength in this first cracking regime and the ultimate cracking regime. So the ratio is between the residual strength and the peak strength. And so the results that we obtained, those are the utility classes that are contemplated by the standards. And for our specimens, we obtained for the unreinforced concrete, the first crack opening displacement, the first index utility is 0.71, and because there is still some load bearing capacity in the first cracking regime, and then this goes basically to 0 for when the crack opening displacement gets larger. And so while in the other materials we got a significant value of this other index, so which means in this case we were able to carry 0.68 of the first crack strength in the post failure regime and the ultimate cracking regime. So the specimens show a significant post-failure, post-cracking load carrying capacity. So the fiber reinforcement ratio, those two quantities, so the increase of those quantities over unreinforced concrete is significant in terms of the first crack ductility, but is dramatically important in terms of the ultimate ductility, because in this case we have increments which are extremely large due to the fact that the plain concrete is a brittle material. We also measure the fracture toughness, which is related to the above quantities, is somewhat related, but it's a different quantity according to the theory of the fracture materials, and this is those are the fracture toughness obtained according to alternative formula. With the fracture toughness measures the area underneath, is a proportional to the area underneath the force crack tip opening displacement, is a measure of the energy dissipation capacity of the material. And what we obtained was that also in this case those quantity were quite larger due to the addition of fibers as compared to the plain concrete. So the energy dissipation capacity was significantly larger. And we also performed some comparisons with the earlier studies on the use of recycled PET fibers, some available literature studies by some Japanese researchers who first examined this kind of reinforcement of concrete, and our results were more or less comparable to the one in the literature. Those are comparisons. Unfortunately, the legend is not visible. This is our curve, and this is the curve of available by those Japanese guy, obtained by the Japanese guy. So we obtained a result that is somewhat comparable in the first cracking regime. Is different in the in the high damaged regime. And we also run comparisons with the commercial fibers, plastic fibers that are available.
Wi-Fi device.
Okay. Oh, you are perfect. Thank you. And also, those are commercial plastic fibers made of virgin plastic. So, industrially produced plastic, which involves production of CO2 and pollution and so on. It's not recycled plastic. And our results were also competitive in comparison with those of using the same fiber volume percent fiber volume content, using the same fiber volume content and commercial fibers or our RPTA fibers, we obtained quite good results in terms of global performance of the specimen, the concrete. In this case, the results were this is okay. In the first crack, in this case, we have a different matching as compared to the one with Also, in this case, what we observe is that our the performance of recycled PET FRC specimens was good in the first cracking regime, and over these other results, these comparison results, we observed a lower residual load carrying capacity, both comparing our RPT fibers with the RPT fibers which had been studied in the literature before, and comparing our fibers to PP, commercial PP fibers that are available on the market. We also run a cost analysis in this case. And what is surprising is that the plastic fibers are not cheap at all. So their cost of steel fibers have a given cost in euro for a cubic meter of material at 1% loading volume fraction. And our fibers, we estimated the cost through the company that was producing the fibers industrially, so they estimated the cost per cubic meter of those recycled fibers, and this cost was much less than the cost of commercial plastic fiber. It could be even 1/4 or 1/2 of the cost of commercial plastic fibers. So the conclusion of this study was that in terms of compressive strength, we had increases varying between 35 and plus 35 plus 16%. We are comparing different PAT reinforcement. In this PAT-A, the high strength, we had the high increases in compressive strength, the first crack strength. In case of PAT-C, we had more reduced increases, lower increases. In the case with this material is in somewhat competitive. This one, which is concrete reinforced with commercial, with virgin PP fibers. And so this is the first presentation about the reinforcement of concrete with recycled PET fibers. The PET, we examined PET in this case for the reinforcement of concrete. And the second lecture, I don't know, at the given time there is a break. I can't remember. But
is there any limit for the use of these fibers?
for the length,
Limit?
yeah, you have to adapt the fibers to the material. Depending on there are many, this work has to be tailored to the concrete that you want to strengthen. So the length of the fibers can be variable, but more importantly, the diameter, the profile of the fibers, and the tensile strength of the fibers needs to be adapted to the concrete. So if you have a high strength concrete, you have to have high strength fibers. If you want to use recycled materials, probably you don't want to reinforce high strength composite. It doesn't make any sense to reinforce a high strength concrete with recycled plastic fibers.
So as in steel fibers, we use only 1.5% fibers.
Volume content, fiber volume content.
After that there is a volume effect in the steel fiber. Same is in this.
Yeah, this percentage was averaged over the literature about similar over available studies in the literature. So you can have 0.5% fiber volume consent from 0.5 to 1.5. This is the usual. So we choose 1%, which is more or less an average value. And but the properties of the fibers, so what we have observed through different studies is that depending on the material you have to tailor the material to the concrete. So the two materials have to be to get along well together, to go along well together, because if you use a given fiber, those fibers were particularly effective because were mixed to a weak concrete. And this is a fact that we have observed in all our studies about the use of recycled materials. So it's recycling through recycled plastic materials, reinforcement through recycled plastic materials is an effective strengthening technique in case of weak concrete, which is the case in most applications, which happens in most applications. For example, not only in the case of developing countries where the nature of concrete is not very high, but also if you want to build industrial floors, if you want to in the industrial floors, so you use a cement which is not particularly performing, but you have to build an industrial floor that can stand concentrated loads due to the machines that can be applied to the floor, and so also for tunnels, for tunneling. So there are several fields of application of these materials that need to be explored. And at that time, we were pretty excited about the results because they were all positive, both in terms of thermal conductivity and the mechanical properties. But what happened is that we were struggling with a huge bad economy for years and years, and those bad economy particularly affected the construction industry. So most companies were not interested in experimenting new materials because there was basically not high demand of concrete materials over the last years. But we hope to recover this project because it's a project that needs to be pushed forward. And this is the first, I think it would be good to conclude the second presentation, which is about the reinforcement through recycled plastic of mortars. In this case, we used a different recycled material. Okay. We used recycled nylon, like the recycled nylon that we employed for fractal fibers, but this study was preliminary to the one that I presented in the first day about the 3D printing of recycled nylon. This was done by ourselves and Ilenia, and we will show you how we obtained the recycled nylon in a very easy way, that by cutting waste fishing nets. We got the fishing nets, we cut pieces manually, Ilenia did that, and she mixed to mortar, and we obtained quite good results. So the motivation is that we are interested in reinforcing cementitious materials with nylon fibers to improve the mechanical strength and the thermal insulation, as we have seen before in the case of concretes. There is plastics everywhere, and there is a huge plastic pollution problem worldwide, especially in the oceans, where finally those products go. And there are some parts of the oceans which are highly polluted due to the presence of plastic materials, mostly plastic bottles, but also fishing nets. Fishing nets are a huge quantity of fishing nets which are abandoned in the oceans, and the numbers are really dramatic. And so the idea was to use those material for reinforcement purposes of cementitious mortars. And because, as we noticed before, the nylon has some hygroscopicity issues, which makes the material more well suited to mortars than concretes. Indeed, this was the case. So there is the existing market of reinforcement of concrete and mortars with plastic fibers is encompasses applications relative to concrete exposed to aggressive environment, and mortar aggressive environments, and mortars for structural rehabilitation. The fibers can be metallic, natural, or plastic. You have to measure the chemical nature of the recycled material. You have to carry leaching tests in order to use a material to reuse a material. You cannot just reuse a material without any care. You have to measure the toxicity of the material. For example, before you can reuse a material, because if it is toxic, you cannot reuse it properly. It's not allowed by the standards. Fishing nets recovered from the seams are not potentially, were proven to be not potentially harmful for the human health. So they were good candidates for recycling materials. What are the advantages of plastic reinforced fibers over steel fibers, which were formerly used for the reinforcement of cementitious materials? Have a higher corrosion resistance, compatibility with additives, and workability as compared to steel fibers, obviously. A lower thermal conductivity, and also lower transportation costs. And so the disadvantage is that they have lower axial rigidity, stiffness, and tensile strength, and they have lower mechanical properties. This is the price you pay, but there are many advantages, We also carried out durability studies in this case. I didn't show before, but for the RPT specimens, we complemented the study that we have seen before for the concrete reinforcement with the RPT fibers we extended the study that I have presented before by immerging some specimens in water for 1 year and measuring the decrease in mechanical properties after 1 year. And we observed good durability results of the fibers, which essentially derived from the fact that the fibers are protected by concrete in the aggressive environment. And so they preserve their properties. In this particular study, I want to describe the cement mortar reinforcement using waste fishing nets. So in Salerno, there is a company that, close to our university, there is a company that recovers fishing nets that are abandoned in the oceans. They are basically, stored by the police in some hangars. This company were using some of this material for recycling purposes, and we obtained some waste fishing nets that we characterized, and we mixed it to a cement mortar. And this was, as in the case of the 3D printed fiber, was a commercial mortar, not a laboratory made. It was a commercial mortar, the same commercial mortar that I have shown before. So I don't want to repeat these considerations about the positive effects of adding fibers to cementitious materials. And which were the tests that we carried out? We conducted the studies on the fibers and on the fiber reinforced mortar. On the fibers, we tested the tensile behavior and durability. And the fiber reinforced mortar, for the mortar reinforced through recycled nylon fibers, we performed bending tests. We also measured we conducted some slump tests to show workability, and then bending tests and compressing tests. In terms of durability, we carried out alkali conditioning of air nylon fibers, and the fibers were obtained by manual cutting of the fishing nets, manual cutting. And we conducted alkali conditioning tests by basically immerging the fibers in an alkali solution, and then we measured the mechanical properties before and after the immersion in the treatment with the alkali solution in order to measure the durability of the material. And we obtained a loss of masses that was not really significant. So the tests were aligned with the tests on PP fibers or other plastic materials, usual polypropylene, or other plastic materials that are used in construction industry. For the tensile tests, we adopted some cardboards because there is a problem in measuring the tensile strength that is well known, because in this lab you work with filaments, and so you test mechanically the filaments. So there is a problem in carrying out tensile tests due to gripping problems. So in most cases you have to run tests on different lengths and different testing lengths, specimens with different lengths, using cardboard tools. And so averaging the results over the three lengths that were considered, we comparing also the results for the material without the alkali conditioning and the alkali condition, we observed a slight decrease in the average tensile strength in the alkali conditioned fibers, unconditioned fibers and conditioned fibers. You can see the difference is not dramatic in terms of the Young modulus and the tensile strength. It's minus 4%, which is in line with the results for most plastic materials. And those are the values obtained for the fibers. Then we mixed the fibers to a commercial mortar, and we obtained, in this case, we considered 1% fiber volume content or 1.5% fiber volume content. The specimens, mortar specimens, are different from the concrete specimens. They are different scale. So in these cases, we tested prismatic specimen with the 40 by 40 by 60, 160 millimeters sides, and we tested two specimens for each different material. We had the reinforced mortar, the nylon reinforced mortar with those are for different lengths. So we examined different cutting lengths. The cutting lengths of 0.51 and 1.5 inches. And so those 0.8, 0.5 are 0.5 inches long fibers with a 1% fiber volume content, 1.5, and so on. And we conducted two tests for each examined material. And this is the mixing process. This is the slump test. This is the slump test, which shows you the fluidity of the material after mixing. And the results were good, were acceptable, pretty acceptable. In the bending test, 3 point in this case on these smaller size specimens of mortars, and we obtained, in this case we obtained both significant increases in terms of the first crack strength, and so plus 60%, plus 18, plus 32, and it increased always by increasing the length, increasing the percentage. We always obtained an increase in the first crack strength, as you can see from this bar diagram. Reinforced PI 0.5 centimeter long fibers, those are the lengths of the fibers. Those are the weight fraction. In this case, we use the weight fraction, not the volume fraction. But it's more or less the same, similar. Those quantities are not much different. We measure the toughness of the materials, and by measuring the energy absorption capacity in the load displacement curve. And in this case, we obtained also, those are the utility indices. We obtained, you can look at those numbers. This is the reduction of the strength post crack propagation. And you see that in this case we can we obtained a 77% recovering of the of the crack strength after crack onset. We also carried the compression test, and also in this case, in this case we measured a decrease of the, in the case of the mortars, we observed a decrease of the compression strength, which is usually standard. You usually obtain reduction of the compression strength and increase in the bending strength. Indeed, this was the case. We had a reduction of the compressive strength in all the examined specimens. So by recycled nylon fibers can improve the mechanical properties, and we observed the significant increases in the first crack strength, and a higher percentage of fiber causes a less significant drop in the load after the peak value. And also the tensile test and conditioned fibers have shown good resistance to chemical attacks and their suitability for application in aggressive environments. So this concludes this second presentation. I have another one, but I think that there is at given point there is a break from, I think that this is the right time for